Hi everyone. In today's video, we're going to talk about notations. We're going to talk about molecular representations, and we're going to specifically introduce one kind of molecular representation that is very important for organic chemistry, which is the bond line structures. So it's my intent in this video that you will be able to interconvert between molecular representations. You'll be able to draw bond line structures, and then you should be able to identify functional groups from molecules drawn using the bond line notation. So let's start with the molecular representations that you're already familiar with. So consider this representation of this particular molecule. We call this representation a Lewis structure. So what I would suggest you do is actually draw out the Lewis structure in your own notebook and take a note of the time it takes to actually draw this thing out completely. This Lewis structure can also be represented as this. In this particular notation, most of the CH bonds are not explicitly drawn, and in fact, they're kind of compressed. We call this a partially condensed structure, but it's just another way of representing the exact same structure that we drew using the Lewis model. Okay, so note that once again, that this is also does take a little bit of time to actually draw. So what I wanted to do is actually draw all of this out. The molecule can also be represented through this particular notation. So this is even further condensed. In fact, no single bonds are explicitly shown in this particular model, but it is still representing the same structure to the left of it. Okay, so this is actually called a condensed structure. But notice that in the condensed structure, we do still have an idea of the connectivity around this particular molecule. Okay. For example, the starred carbon on the condensed structure is equivalent to this starred carbon on the partially condensed structure and to that starred carbon on the Lewis structure. And this starred carbon in the condensed structure is connected to a hydrogen, an oxygen, and two carbons in your CH3, in your parenthesized CH3 group. And then lastly, the other notation is essentially a molecular formula. Note that the molecular formula, although it is easy to write out, it contains no bonding information whatsoever. Okay, and so each of these molecular representations kind of brings something new to the table. Lewis structures are explicit. You can see all the bonding patterns. Partially condensed structure are slightly more convenient to draw out than Lewis structures. Condensed structures are a little bit more convenient to write out. However, they become a little bit harder to read, especially for larger organic molecules. And certainly, molecular formula will do no good in giving you bonding information once you go beyond two carbons. Okay, however, the key thing to realize here is that since in organic chemistry we deal with pretty large and sometimes fairly complex molecules containing a multitude of carbons and specifically smaller other heteroatoms like oxygen, nitrogen, and fluorine, none of these notations are actually fairly convenient. You have to spend a lot of time drawing Lewis structures and a lot of time drawing partially condensed structures in order to account for the complexity of organic systems that we'll be looking at. So there is a new notation that I'm going to show you that would help in reducing the time spent drawing organic molecules, but do require some level of interpretation in order to understand and draw it efficiently. And to introduce this notation, we're going to use this particular molecule, which has four carbons in a linear chain and 10 hydrogens around the four carbons. In the current form, this particular molecule is represented as a Lewis structure. And it can also be condensed into its condensed formula. So notice here once again that there are no explicit bonds shown, but you can still tell the connectivity of the four carbon atoms and the hydrogens where they're connected to. Also note that the condensed formula can also be written as such, where that parentheses and the subscript 2 that flanks that CH2 tells us that there are two CH2 groups in a linear chain sort of going in between the CH3 and the CH3 on the left and the right, respectively. Now, what I have drawn on the right-hand side is actually the exact same molecule, but in its bond line notation. And notice right off the bat that things look very different from the Lewis structure, where we're not really seeing any of the carbons or the hydrogen atoms on this particular molecule. And so we will make note here that for bond line structures, the carbon chain is drawn in a zigzag way. So notice that instead of having everything look like they're linear, we actually see the bent geometry, if you will, around every carbon on this chain. And then also notice that the corners of the bond line structure, so where I have starred on the structure, these all represent the carbon atoms. So if you look at a Lewis structure, we see that there are four carbon atoms. And so on our bond line structure, we have on each corner, there are four corners of a bond line structure. And then thirdly, the CH bonds that we should expect to see from our Lewis structure are not actually explicitly drawn in our bond line structure, but we can infer the number of CH bonds around each carbon by taking the number 4, which is how many bonds we expect a neutral carbon to have, and removing or minusing out the number of explicitly shown bonds on the bond line structure. So for example, if you take the carbons on positions A and D on the bond line structure, you would see that on these carbons, we are explicitly showing one bond. So for a neutral carbon on that position A and D, we subtract out 1 from 4, and so we should expect that there should be 3 CH bonds on A and D. You can call these groups CH3 groups, and this is exactly what we see in our Lewis structure. And also, carbons B and C, these carbons on those corners, you can already explicitly see 2 bonds drawn to those carbons, which means that we should expect 2 additional CH bonds on those positions because these are neutral carbons where we should expect 4 bonds around each carbon atom. And so we can think about the carbons on B and C positions on this bond line structure as CH2 groups. And so once again, you see how we can then imagine our Lewis structure by just looking at the bond line structure, but it makes drawing organic molecules, which are primarily carbon-based molecules, easier to draw rather than having to explicitly show all the carbon and hydrogen atoms in your molecule. Okay, so now here are two examples of molecules in which I have drawn out the Lewis structure. And what we're going to do is try to draw out at least one example of the condensed formula and what the bond line structure will look like. So for the first molecule, we notice that's a pretty long chain and it has double bonds, triple bonds in there. So it is best in this case to actually number your higher valency atoms, so in this case your carbon atoms, just so that you can make sure that you are tracking what they look like when they are converted into the different molecular representations. Okay, so on my end, I count 8 carbons going from left to right, and carbons 2 and 3 is where we have the double bond, and carbons 6 and 7 is where we have the triple bond. So the key thing to remember in this particular condensed formula is that we do need to explicitly show the double and triple bonds here, even though the single bonds are not explicitly shown. So our carbon 1 is the one with the CH3 group. Our carbons 2 and 3 are shown right here, and you notice that the double bond is explicitly shown in that particular chain. Carbons 4 and 5 are explicitly shown right there. For carbon 6 and 7, we explicitly show the triple bond. And lastly, carbon 8 is at the end with its CH3 group. Okay, and now we're going to draw this into the bond line structure.
So remember that we do everything in zigzag. So carbons 1 through 6 are going to be in zigzag. However, the key thing to note that is a little bit different is that because carbon 6 and 7 are sp hybridized carbons, those are going to be linear. And so we're not going to zigzag 6 and 7. So I'm going to show you what this looks like, but you want to follow along as well. So here's carbons 1 and 2. 2 is bonded to 3 as a double bond. Remember that we're not showing the carbons or the hydrogens bonded to the carbons. 4 and 5 are shown right here. They're just CH2 groups. Now here's carbon 6. Carbon 6 is unlike the other carbons 1 through 5 because carbon 6 is sp hybridized. We expect the geometry around 6 to be linear. And so we're going to draw out a linear line, no bending at that carbon 6. Okay, and so we notice that carbon 6, there's no bending. Carbon 7 as well, there should not be any bending because that's a sp hybridized carbon. So we're going to just keep on drawing the line in the upward diagonal direction to finish off with carbon 8. Okay, so notice here once again that everything is zigzag except for 6 and 7 because of those sp hybridized carbons on that particular position. Okay, so now let's look at the third example. So this time we have a different atom in this molecule. We have an oxygen as opposed to all carbons and hydrogens. And so we're going to see how that plays out in the condensed and bond line structures. Okay, so for a condensed formula, there are actually several ways you can draw a condensed formula. So I'm just going to show you two of them, just so you can see how they can all be drawn and they will all be correct. Okay, so here's one example of our condensed formula. And what I have done here is to highlight where those CH3 groups are in our Lewis structure and where it is in our condensed formula. So notice that we're flanking the two CH2 groups on both ends, and in between there's a carbon hydrogen group, and there's an additional branched out OH group, which we are putting in parentheses. And so that would consider, in this case, is considered a branched out group in our condensed formula. So here's another example of a condensed formula, which would also be equally correct. So in this case, we are representing almost as if the carbon in the middle, the CH group, is sort of our only chain, and the two CH3 groups are sort of branching out of that middle carbon. So in this case, the two CH3 groups are sort of condensed into its parentheses with a subscript 2, which is telling us that there are two CH3 groups that are bonded to the CH group in the middle, and then our OH group is sort of placed on the right-hand side. So there, once again, there's several ways to do a condensed formula. The key thing is to ensure that your connectivity is correct and that you are following some of the conventions when it comes to when to show a bond and when not to show a bond. Now, I want to show you the bond line structure. Okay, so here's the bond line structure. And I've once again highlighted out those two CH3 groups that are in our Lewis structure. And once again, notice the way we are drawing it. We zigzag our carbons, and each carbon is at the corner of your bond line. So notice here that the hydrogen on the oxygen is explicitly drawn, and that has to be drawn. So the only hydrogens we do not need to draw in a bond line structure are the ones bonded to the carbons. But every other atom that has a hydrogen, that hydrogen needs to be shown on your bond line.
We're going to go through more examples. This time, we're going to understand how to draw bond line structures that contain formal charges. So what I have drawn here is an example of a Lewis structure with a formal charge in that middle carbon. So that middle carbon has only three bonds, two of them to carbons and one to hydrogen, and no lone pairs on that carbon. So that is a positively charged carbon or a electron deficient carbon. So, in order to depict this particular molecule using the bond line notation, we can simply use our zigzag format again. However, formal charges must, and this is a big must, it must be explicitly drawn on the atom that indeed has a formal charge. Because this is the only way we're going to be able to re-represent this structure back as a Lewis structure is by truly and explicitly and unambiguously placing the formal charge on the particular middle carbon and not anywhere else in this molecule. So here's another example. This time, the carbon in the middle is bonded to three atoms, so two to carbon and one to a hydrogen. So there are three bonds around that carbon. However, it has a lone pair. So there's actually one more electron on that carbon than it should have, which means that it has a formal charge of -1. And note that we've explicitly shown the formal charge -1 on that particular carbon. Once again, when you're trying to represent this as a bond line structure, you draw out the zigzag formats, but once again, you explicitly show that there's a formal charge, in this case, -1 on the middle carbon. The reason why this is important is that realizing that a carbon with a positive formal charge and a carbon with a negative formal charge both have three bonds around that carbon. So whether it's a positive or a negative, you should expect only three bonds around the carbon. The one thing that is different with a carbon with a positive charge versus a carbon with a negative charge is that a carbon with a negative charge has an extra lone pair on that carbon, while a carbon with a positive charge has no lone pair on that carbon. So here's another example. So now we're dealing with charges, the formal charges on heteroatoms. So atoms that are not carbon or hydrogen. And here is the bond line representation of the Lewis structure to the left. Okay, so note a couple of things. There are no CH bonds on the carbon I have specifically highlighted here. In the neutral oxygen, there are two lone pairs that are not shown. However, in the negatively charged oxygen, there are three lone pairs that are not shown here. Okay, so once again, in the bond line structure, we do not have to show the lone pairs. However, you have to know how many lone pairs are in each of these atoms, right? So this starts from understanding valency, understanding the generic Lewis structure for neutral atoms, and then looking at how this is changed when you increase or decrease the formal charge. Okay, so for your own exercise that I want you to do and practice on your own is to draw the condensed structure and the bond line structure of the following compounds before we keep going. Okay, so lastly in this video, we're going to introduce the concept of functional groups in organic chemistry. So a functional group is a characteristic group of atoms or bonds or both that possess a predictable chemical behavior. So remember from class, I've sort of started introducing the idea that organic chemistry is all about patterns. And so if you're able to see structural patterns in organic molecules, you can start to predict their chemical behavior. And so for now, what I'm going to show you are common patterns that we're going to talk about for the rest of this academic year. And so just to get a good sense of what they are at this very moment. Okay, so we're going to go through some examples, and these examples are in your textbook. So I actually really encourage you to look more deeply into these in the textbook in chapter 2. And note that R, whenever I draw R here, is really just the remainder of the molecule. So the first one I'm showing here are these RX groups, where X equals to chlorine, bromine, or iodines. We call these your alkyl halides. Whenever you have a halide connected to a carbon, where this is called an alkyl halide. Then we have sort of our family of double and triple bonds. Though when you see a double bond in organic chemistry, we call these an alkene. And if you see a triple bond in organic chemistry, we call this an alkyne. So once again, that's just a notation. R is just whatever is the rest of the molecule. Next, we have our bonds to oxygens and bonds to sulfurs. So if you have a bond to an oxygen and the oxygen is bound to a hydrogen, that's called an alcohol. Okay, so we have these alcohol groups. If that bond to the oxygen is also bonded to another carbon, so an ROR functional group, we call that an ether. On the sulfur end, R bonded to sulfur, which is bonded to another R, is called a sulfide. And an R bonded to sulfur, which is bonded to a hydrogen, is called a thiol. All right, so in the case of an unusual and in fact somewhat special functional group, we have this six-membered ring where you have your six carbons in alternating single and double bonds. We call these aromatic functional groups or arene functional groups. Okay, and then we get into what we call the carbonyl family. So the C double bond O family. And in these cases, there are quite a lot. So we're going to start with the standard and maybe in many ways the parent functional groups. So you have your RC double bond O, and that C is bonded to another R. We call it a ketone. If one of the R groups are replaced with a hydrogen, we call that an aldehyde. And then here's the rest of the family. Like I said, there are a lot. So you have your carboxylic acids, where that R group from your ketone is replaced with an OH group. Now you have a carboxylic acid. You have your acyl halide, if that R group from the ketone is replaced with a halide. You have your anhydride, if that R group from your ketone is replaced by what we call a carboxylate group. So it's essentially an O single bond to C, double bond to an O, and that carbon is then single bonded to another R. If your R group is replaced with an OR group, so it's an oxygen bonded to another R, that's an ester. And then if you have your R group replaced with a nitrogen, which is bonded to two R's, just the rest of the molecule, we call that an amide. And lastly, if you just have a nitrogen bonded to three R groups, the R's once again could be carbon or hydrogen or the rest of the molecule, amines. So AMINE. Okay, so notice that this is a juggernaut, right? There's a lot of these functional groups, but it's important once again to start to see some patterns, how you can group these functional groups to help you in remembering what they are. And in many ways, by grouping them, you can also kind of see how some of these can react in very similar ways. So they will have very similar predicted chemical behaviors. Okay, so here's a molecule in which we're going to try to dissect this molecule into its functional groups. So what I might suggest you do is either refer to your textbook with the table in your textbook, or you refer to the previous scene in this video for your reference. But to dissect this, there are actually five functional groups in this particular molecule. And so if you can see them, you're on your way to mastering functional group identification. And I have circled the five functional groups in this particular molecule. And now I have labeled them based off of the functional group identification and classification in the previous scene. So from the left to the right, we have your amine, your alcohol, your ether, your arene groups, which is your aromatic groups, and you have your amide group. Okay, so it's important you're actually able to see on the bond line representation these different functional groups, because that would then be really helpful as you're thinking about chemical reactivity and how these things will react to other molecules. Okay, so it's my hope once again that you are able to interconvert between molecular representations. You've been able to draw bond line structures and convert between bond line structures to condensed structures to Lewis structures. And then you've been introduced to functional groups and you're able to sort of identify or begin to identify functional groups in larger and somewhat more complex organic molecules. Okay, thank you so much for watching, and I will see you in class.